Okay, we were talking about patterns, and we went over the abstraction-occurrence pattern, which is one of the key patterns that you find in many class diagrams. I showed you several examples of that, which are shown here on slide 5, where, for example, we have an abstraction. The TV series has a number of occurrences, the episodes, and the abstraction, the title of a book, the title has many abstractions, books, the library items, which you can actually borrow and have barcode numbers. And we looked at a number of ways this shouldn't be done. In particular, you should not make a subclass of the abstraction. Okay, that is a very typical error. Okay, people think often that this might be the case, but it's definitely a problem, and it's very important for you to understand why this is a problem. Once you begin to see why these things are problems, at that point you can begin, a lot of this stuff is really sinking in, okay? This diagram on slide 7 shows two occurrences of the abstraction-occurrence pattern. I call this the abstraction-occurrence square variant, because what we're seeing here is a pattern which occurs quite commonly in scheduling applications. So what we have is again, this notion of the scheduled thing and the specific thing. We saw that in the airline system. We have a scheduled, a regular flight, and then the specific flight, which is the occurrence that goes on a particular day. So here we see it in the train domain. You can see it in the bus domain. Any kind of scheduling domain, you very often see this. The abstract schedule that is repeated, and then the individual repetitions, okay, on a particular date. Now, the interesting thing is that what we can do in a train or airplane situation as well, or bus situation, is we can say, well, the scheduled train, which say runs from Toronto to Ottawa, let's say, stops at various places, including Kingston. Okay, so let's just say it's an express train that only stops at Kingston and then goes to Ottawa. So it's got two legs, and each of those legs has a separate schedule. So the train itself is scheduled; it has a train number, but it's also got a separate schedule for each leg: a departure time from Toronto and an arrival time in Kingston, and a departure time from Kingston, arrival time in Ottawa. Okay, and we can in fact say that these two legs are indeed parts of the overall schedule. We can use the diamond symbol for the aggregation there, and there can be any number of these scheduled legs. These probably should be 1 to star, in fact. And the legs have things like a station and origin and destination. Now, moving on from that, we can also see that when we go for a specific train, okay, a specific train which has a date, it has also parallel legs, okay, because the one that is leaving today from Toronto and arriving in Kingston at the scheduled, supposedly at the scheduled departure time and scheduled arrival time, has an actual departure time and actual arrival time, or expected arrival time, you might put it down, which might be later, usually would be either the same or later, okay, and this is quite important to people who are actually traveling. The scheduled arrival time is important too, but the actual or expected arrival time is also important. Okay, and that applies differently on a daily basis from the normal schedule, which is what we see over on the left. So again, we have an abstraction occurrence here. We have the abstract schedule for the leg, and the occurrence, the specific occurrence of the timings for that particular leg. Okay, this actual specific leg is also quite important for a number of other things. For example, you know, the capacity control, how many people are on the train. You know, you can't sort of say, well, the train takes 250 passengers, and therefore we'll put the maximum size of the overall train as 250. What matters is each leg, because what if, you know, a lot of people get on at Kingston and fewer get off? Well, then you might overload the train. So the number of people on each leg is particularly important. Okay, so if they're selling tickets, they have to keep track of where people are going and how many are on each leg at any given point in time. So you can add attributes like total seats sold here in specific leg. Okay, so the point is that we have different classes with different attributes needed in each class, and two parallel abstraction occurrences together. Something that you see in scheduling applications. Any questions? Okay, well I hope you've understood the abstraction occurrence. We're going to move on now to another pattern. This pattern is called the general hierarchy pattern by me. It's also called the composite pattern in the Gang of Four book, although the composite pattern is described a little bit more specifically, and I've generalized it slightly, calling it the general hierarchy pattern. Okay? The idea is that we have objects in a hierarchy. Now, we're not talking about an inheritance hierarchy. We're not talking about classes in a hierarchy. And we're not talking about an aggregation hierarchy, okay, which is a hierarchy linked by associations. We're talking about objects in a hierarchy. So the linkages are by links, okay, in an instance diagram. Objects in a hierarchy can have one or more objects above them and one or more objects below them, okay? So, and hierarchies are very common in ordinary ordinary domains. So you have organization charts, so a typical example of a hierarchy, okay? But you have many, many other kinds of hierarchies out there in the world as well. We can call the objects above the superiors, the objects below the subordinates. Some hierarchies are strict hierarchies, where they have many subordinates, but only one superior. Other hierarchies sometimes allow multiple superiors. Okay, that can be an extension of this. And some objects cannot have any subordinates. Okay, they're often called leaves, and the object at the top of the hierarchy, or objects if there's more than one, also cannot have superiors, which should be indicated here, I guess. Okay, so the problem is, in general, how do you represent a hierarchy of objects? Okay, we're not talking again about a hierarchy of classes. We know how to do that. That's a generalization hierarchy. We're talking about a hierarchy of objects. Now, there's a number of different ways of doing this. I'm going to show you one that is quite common, and that is the general hierarchy pattern. Forces. Remember we said the forces are these qualities that we're trying to balance, you know. In this case, one of the qualities is flexibility. We want a flexible way of representing hierarchies. So we can easily add new nodes at different points in the hierarchy, and so that we aren't hard-coding too much stuff. Okay, we also perhaps want to prevent certain kinds of objects from having subordinates. Okay, so if we have certain classes that do have subordinates and certain classes that do not, we want to see if we can represent that concept as well. Okay, and all the objects have common properties and operations. So there's something about each of these nodes in this hierarchy that is common. They're not different in unrelated ways. They're closely related to each other. So in an organizational chart, everybody's a person, and more specifically, everybody's an employee. Okay? And so as an employee, you work for a company, you have a salary and things like that. So there's lots in common among the elements in the hierarchy. But nevertheless, they are hierarchicalized in some way. Okay, so this diagram at the top of slide 9 then is the abstract pattern for the general hierarchy that we're going to be looking at. We have nodes. Okay, in general, everything is a node. So we're showing an inheritance hierarchy of 3 different kinds of nodes. Okay, this inheritance hierarchy is not the hierarchy we're talking about in the general hierarchy pattern. Okay, this is a hierarchy of classes, and these nodes are put together to form hierarchies of instances. So in general, there are nodes, and those nodes can be of at least 2 different types. Okay, there could be one. In fact, there could be just one subclass, but I'm showing 2 to illustrate there's 2 different typical types of subclasses. We have the non-superior node classes, which means nodes which don't have which don't act as superior nodes, and which don't have subordinates, and nodes which can act as superior nodes, nodes which can have their own children in the instance hierarchy. Okay, and these superior nodes are the ones that have an association to other nodes. Okay, so let's just schematically show this on the board for just a second here. As instances, okay, we have some. This might be a superior node. This might be a non-superior node, but this might be a superior node, and so we might have non-superior and non-superior as the leaves. Okay? Okay, so superior nodes are ones that can have children, and these ones sort of terminate at the bottom. There are huge numbers of examples of these in many real applications. For example, you may not have studied grammars yet. That is a topic which will be discussed in the next course, SEG 2101 at the University of Ottawa. And one of the things that we find out is that we have terminal and non-terminal structures in a grammar. Okay, so the individual words in sentences become the terminals, and the non-terminals are the higher level structures like verb phrases and sentences and things like that. Okay, so this is the kind of thing that we see over and over and over again in computer science and software engineering. Down at the bottom of slide 9, there are two examples. Okay, we have a hierarchy of different kinds of employees. Okay, this is not an org chart, right? This is a hierarchy that is describing the nodes that could be in an org chart. In an org chart, we would have many different layers potentially. So in this little inheritance hierarchy, everybody's an employee, and this organization says, well, there are three particular classes of employees: secretaries, technicians, and managers. Okay, so the secretaries maybe have certain kinds of attributes. The technicians maybe have responsibilities for certain technical responsibilities, and the managers have other things associated with them. To justify having these three classes, there would have to be some attributes, some operations, and or some associations, not shown here, that would mean that there's the need for the three classes. But given there's the three needs, one of the things we can say is that the managers are the ones that have supervision roles over employees. So managers supervise employees. And so what we can do now is we can go back to this diagram here. Let me just get an eraser. And we can say, well, it could well be that this is a manager, and this is a manager, and this is a technician that reports to that manager. This is a secretary, and this is a technician that reports to that manager. Okay? So these will be instances that might be derived, or this, we can say this is an instance diagram that could be generated from the class diagram on the bottom left of slide 9. Okay? There could be many levels of depth as well. In a large organization, there could be 5, 6, 7 levels of management. Okay? Does anybody not see how this instance diagram relates to this class diagram? It's very important that you understand that. Okay, all of these links are links of the Supervisors Association. Okay? Another example comes from the domain of operating systems, where we have a bunch of file system items. These are items that have a name, they have a date modified, and various other kinds of attributes associated with them at the general level. And there are then several different kinds of file system items, and we categorize them here into just two classes: the files and the directories, or otherwise known as folders in some operating systems. Okay, so files are the terminal cases, they are the non-superior nodes, and the directories can be hierarchically related at any number of levels. And each can contain any number of other file system items, which could be files or directories. So this recursively goes down until we get to files or directories that are empty. And you'll notice that this is 0 to star, therefore there could be an empty directory at the bottom. That's perfectly possible. I'm also showing a diamond here indicating this is an aggregation. And so it's quite common for these hierarchies to be showing the aggregation relationships. So the file systems items we can say are part of a directory. Okay, that's a legitimate aggregation. But I wouldn't say that a manager, that an employee is part of a manager. Therefore, I didn't use the aggregation in the org chart class diagram on the left. Okay. And this is one of the things which distinguishes this generalized hierarchy pattern from the composite pattern in the Gang of Four book, because the Gang of Four book tends to focus on the cases where they are aggregations. Okay, any questions about this pattern so far? This is a very common way of doing hierarchies as class diagrams. It's showing class diagrams that will generate instance hierarchies when you actually run the system. Any questions about that? Very important, classic design pattern. Yeah?
Yes, and what's the difference between this and generalization?
This thing here, okay, is what I call an instance hierarchy, okay? It's an instance hierarchy. There's no generalization here. You can't say a secretary is a manager. You can't say a technician is a manager. So this is definitely not a generalization hierarchy, right? That's clear enough. Okay? These things over here are. These things over here are class diagrams that contain a generalization. No problem. The diagrams on slide 9 definitely are generalizations. But what I'm talking about is and this is why you require a little bit of thought of understanding. It's in some sense it's irrelevant that what we have here it happens to be a generalization. That's not what I'm interested in. I'm interested now in these hierarchies, these instance hierarchies, okay? And how do I generate those? Does that make things clearer? You might call this a hierarchy at the meta level, and this is the hierarchy at the ordinary object level. But sometimes getting your mind around these things, hierarchies that generate other hierarchies, can sometimes be a little bit tricky. And we saw another example earlier on where we can have hierarchies of instances, and this is a typical anti-pattern. Okay, this is on slide 10 showing different subclasses using generalization instead of using the general hierarchy pattern. Okay, so what we should have done is we should have said that we have some kind of recording. Okay, and then there should be an association into that, okay, which is saying with the subordinate relation, okay. So the subordinate relation into that is, say, subcategory, okay, and then we might have some subclasses of this, okay. Now we would only have the subclasses if there was a legitimate need to have classes that then couldn't be broken down into into further detail. So we might conceivably here have some very detailed category, like music by a particular musician or something like that, and then this is the general categories like classical and so on. There is another way of doing a class diagram for hierarchies, and that is to dispense with these subclasses entirely and to just use a reflexive association. Okay? So in situations where you don't need the subclasses, okay, like the secretaries, technicians, managers, or files directories, you can also do a hierarchy as I've shown here, using a reflexive association. Okay, and that, in fact, if you look back to the diagram we saw much earlier on in chapter 5, is how we did a hierarchy at that point, a hierarchy of recordings. Any questions? Okay, let's move on to another pattern, the player role pattern. These first three patterns, by the way, abstraction-occurrence, general hierarchy, player role, are patterns that are helping us solve problems that are very, very common, mistakes people make that are very, very common in class diagrams. A little bit later on we're going to get into patterns that help us do interesting aspects of architectural design. But these patterns are patterns that are found all the way back into, especially abstraction-occurrence in general hierarchy, they're found all the way back into domain analysis. Here, the player role, we're beginning to get into a pattern which is probably more typically employed when we're doing a system domain diagram, where we're not modeling the real world quite so much, but the data about the real world. But this pattern here is a pattern that will solve a number of problems that we alluded to in chapter 5. And in fact, we've already seen a case of this. A role is a particular set of properties associated with an object in a certain context. Okay, so it's a set of properties associated with an object. And an object may play different roles in different contexts. Okay, so you can think of play a role in a card game. You've got the dealer that plays a particular role at certain times, and then you've got maybe the shuffler that plays a role, and you've got the other players. Okay, so you've got 3 roles played, and the dealer will change as the game rotates. A different person will become the dealer. A different person will shuffle the cards. Okay. You have many other circumstances where people change their role. Okay, you might very well at some point be a regular employee. Later on, you become a manager. Okay, so again, you could change role. In fact, the hierarchy of different types of employee that we saw in the previous pattern could very well become a hierarchy of roles instead, where we have the employee role and then technician role, secretary role, manager role, because the secretary could be promoted to become a manager, so could the technician. Okay, and they would have to change roles at that time. So the big problem then, if we want to model roles, is how do we best model players and roles so that the player can change roles, because secretaries do get promoted to become managers, and possess multiple roles. Okay, so that I can do more than one thing at a time. Maybe I'm not both a secretary and a technician at the same time. In that application, maybe you don't need this second part. But there are situations like being a herbivore and being a carnivore that are needed at the same time. Okay, and I want to be able to show the 2 different groups of properties, the herbivore properties and the carnivore properties associated with a particular animal. In that case, animals maybe won't change roles. Okay, they may have a fixed role, but in that case, they possess multiple roles. So this player role pattern has to do with being able to change roles and being able to play or possess multiple roles. And the pattern can be used in either circumstance when we have either kind of problem. What's wrong with ordinary, just simple class diagramming as we've done? Well, we saw that back in Chapter 5. Go back and look at some of the earlier slides. You'll see that we said that, for example, if I have graduate student and undergraduate student, I don't want to have to change instances. I don't want to have to take an instance of graduate student and delete them and add a new instance of undergrad if they take another degree, or vice versa. So what does the pattern look like as a class diagram? Well, at the bottom of slide 12, we see we have some kind of class we're going to call player. Associated with it, some kind of hierarchy of classes. Generally speaking, a hierarchy, because you want more than one role. So the notion is you've got an abstract role, and then one or more, usually 2 or more, subclasses of abstract role, and we're going to call them role 1, role 2, role 3, etc. Multiplicity here could be 1-to-1. Okay, meaning I can only take on one role, and I always have a role. It could be 1-to-many, meaning I could have several roles. Okay. It could be 1-to-0-to-1, meaning I may or may not have any role, depending. So I haven't shown multiplicity, but the multiplicity has to be independently chosen based on the application. The forces involved in this, okay? One of the forces is improving encapsulation. Okay, we want to be able to separately program roles, develop the role. Maybe individual programmers are responsible for each role. Okay, the information about a role is programmed and encapsulated in a different class. Okay. Now I could do that by having subclasses of player, but if I did that, then I would end up with possible situations where our instances have to change class. So one of the forces is you cannot allow an instance to change class. And then the third thing is you want to avoid multiple inheritance. So sometimes you need to divide up the classes in multiple ways, and you end up with multiple inheritance. We said you want to avoid multiple inheritance. Well, what you can have is instead of multiple inheritance, you can have multiple player role patterns. So I can have one, maybe the type of food the animals eat carnivore, herbivore, etc., is one of these hierarchies. And then ticking off the other side of the animal class is the habitat. So are they water-based, are they land-based, etc. And by the way, some animals can change habitat as they develop. Some start in the water and then come on land, things like that. So you can imagine this could be quite useful in modeling properties of different kinds of species. Any questions before we see the concrete examples? Usually the concrete examples are what make these diagrams much clearer, what make these problems much clearer. Here is, in fact, the animal problem. Okay? So I'm showing now a situation where I basically have two discriminators, type of food and habitat. And instead of using multiple inheritance, what I'm doing is I'm choosing one of the discriminators to become a discriminator on a hierarchy of roles. So what I'm saying is that, well, animals are carnivores, herbivores, and omnivores, and that's the sort of fixed property of them. So I'm using an ordinary generalization for that. I could have used another role hierarchy, but I'm using an ordinary generalization. And then I'm saying, well, the habitat changes. Some animals sort of grow up when they're infants in the water and then become land animals. And so what I'm doing is I'm deciding that I will have roles attached to these, and I can have either one role or a second role. I can maybe have both if it's the word is slipping me there. The amphibious. It's an amphibious animal, right? Or I can change it during the lifetime of an animal. Okay, if the animal is one of these ones that changes at different points in time. And I'm saying here, multiplicity 0 to 2. Okay, so an animal may not have any habitats. That's kind of strange. Probably should have some habitat. Maybe I'm allowing 0 in case at some point in time I haven't figured out what it is. And up to 2. So I may have one instance of aquatic animal and one instance of land animal attached to the animal. Okay? It's important to understand how these things translate into instance diagrams. Okay? So at the instance level, it might well be that the animal itself is strictly abstract. I haven't shown it in italics here, but let's imagine that animal is abstract. Okay, so then I have a carnivore. Okay, and so I might have an instance of carnivore. It might in fact be wolf, let's say. Okay, maybe what I'm doing is modeling species here. So wolf, okay, the carnivore. And associated with it is its role, the role it plays in the ecosystem. The habitat role it plays in the ecosystem. It is a land animal. Okay, so I'm going to have associated with that an instance of. This should be underlined. An instance of land animal. Okay, and then I might have some properties of. I'm not a biologist, but I could imagine that land animals have certain distinct kinds of properties. Okay? Certainly aquatic animal you might put of a salinity of water it likes and things like that. Land animal you might say does it live in grasslands or trees or whatever. Okay? And so this would be the example of how this might map into a real. This is the role that this animal plays. Okay? Yes?
When we were putting player and role and animal and habitat role, why we always have one on the side of the player? Why can't we have many-to-many relationship or many-to-0-1, 0-2?
What you're saying is why can't there be a many right next to animal? Okay. What you're then saying is that a particular role can be the role of many of the players. A role can have many players. That I would say that would be certainly possible. It depends on a number of aspects of what you're trying to model here. The tendency is that what we're modeling here is individual situations. So, for example, we have an employee and they have roles, a role as secretary, role as manager, etc. And in that case, I want, as my particular role as manager, I supervise certain employees and I have a certain responsibility for certain projects. And therefore, this data, the role data, is data about me specifically, so one of the players. But if I was being general and I was just saying, well, you know, there are certain animals, certain land animals that live in dens, let's say. Okay, well then obviously, in that case, we're using the habitat role as something which could apply to many different species. Okay, and in that case, you're right, this could be a many-to-many relation, sure. Absolutely. Okay, the important thing is not what the multiplicity is, that can vary. The important thing is using the role classes to add details that can change or to avoid multiple inheritance. Other questions? I saw somebody's hand in the back over here. Yeah?
Wouldn't an instant of abstraction role belong to only an instant of animal? So
I just explained, he said, wouldn't an instance of habitat role only belong to an instance of animal? Well, the answer is that it could belong theoretically to more than one. It depends on how you're modeling this system. Okay? It depends on the kind of information you want to store. Okay? And one of the things here is this a species, I'm showing it here as species. I should have probably called this animal species. If I'm modeling taxonomy in biology, that's what I was doing. If I was doing this in a zoo, and keeping track of individual animals, and the particular food that the individual animal likes, for example, and their name and things like that, okay, then I might very well be dealing not with general habitats, but with specific habitats. And so I have a particular body of water in my zoo, and I'm saying where that particular animal is, and a particular body of land, and where that animal is, you know, so on. And the temperature that this is the water temperature, and other things that I have to put into that water and stuff like that. So we could go into more detail depending on exactly the kind of problem I was solving here. But in general, the issue is not that level of detail. The issue here is that we can have the roles. Okay. Any other questions? Okay. Another example. Okay, and again, we saw the example of full-time and part-time students in Chapter 5, and we said that, well, students do change from full-time to part-time, from part-time to full-time, and they change from undergraduate to graduate quite often. Sometimes the other way around. You know, you take a master's or something, and then you go and do a law degree, and law degree is considered undergraduate. So, hey, all kinds of possibilities allowed here. So what I'm saying here is instead of doing what I did in the previous example of having subclasses of one and the roles for the other discriminator, I'm creating two separate player role patterns here. Perfectly legitimate. I'm saying that a student has one of these, full-time, part-time, and these individual objects might be used for computing things like the fees I pay and stuff like that. On the other side, I have one of graduate and undergraduate. Again, might be used for computing fees or something to do with what courses I'm allowed to take, what rules apply to me, etc. Okay? As always, there have to be legitimate differences between these pairs of subclasses in order to justify the existence there. Okay, so that's the second example. Anti-patterns. One anti-pattern, merge all the properties into a single player class and not have role classes at all. Now that's an anti-pattern if you're going to make an excessively complex class. If the class is simple, very, very simple, it could be justified. But quite often what people do is that they see that multiple inheritance mess showing up, and they say, well, okay, we're just going to merge everything into one class. And that often results in too much complexity, and you don't have the modularization that you want. And then another anti-pattern is to have roles as subclasses of the player class. Well, that's what we saw in Chapter 5. So I have my students, and then I have my undergraduate and graduate students as subclasses. And then we get back into we haven't solved the problem. We have the problem of changing instances at runtime. Okay, we'll move on now to another pattern, and as we move through these patterns, we're getting steadily deeper into design. Okay? The Singleton pattern is a pattern that you often introduce a little bit later on in the development of your system. It often doesn't show up very early. The Singleton pattern is a situation where you have a class with one instance. Okay, we know that there's, for example, in a bank account management system, there may very well be just one bank. In the university registration system, the system that there's many universities in Canada, many universities in the world, but we're not modeling all of those. We are at the University of Ottawa setting up the registration system for students here. There's only one university here. And therefore, if we're going to model university, it's got one instance. And then, what are the implications of that? That is the Singleton pattern. That's the context. The problem, and it's a design problem, it's not so much a modeling problem. The design problem is, how do we ensure that it's never possible to actually accidentally, programmatically, using a bug or whatever, create more than one instance of this class? We would like to protect our system from accidentally duplicating the university and having two University of Ottawas by mistake. Okay, and this pattern gives us a simple way of doing that. Okay, forces now, one force is a constraint in the programming language. Okay, if you have a constructor to create objects, and it's public, because you do maybe have to have on the API a thing that says, okay, we're going to start building our data. Create the first university, and then I'll start adding students to it, or adding courses, or adding professors. So I've got to create the university first when I start the system running, the very first time. So in some sense it should be public, perhaps. But if it is public, then you can't guarantee that it won't get called twice. Okay, so maybe we shouldn't have a public constructor. That probably sounds like a bad idea. So this is a force that comes out of the nature of the programming language and the rules that cause us to think a little bit about how we do things. Second situation is that we do need access to this instance, okay? It is the university class, typically, or the Singleton class, that is the class where we do a lot of our main queries out of. Tell me how many students there are. Well, I'm going to ask the university to count the students. There might well be a situation in the diagram, okay, where we've got university, Singleton class, has many students. Okay, so this is the, where you store the students. I mean, this tells us that there are many of them. Okay, if I didn't have this, I wouldn't know if it's just one student or not. So this is telling us there's more than one of them. And if I'm doing queries, find me the student named, some particular name, Muhammad Ali, okay? Well, then, I'm going to search in the university, and that search is going to look at all the links, right? And so I will need this class, and this class will have to be accessible publicly. Because I'm going to have to say, the university, please find this student. Or the university, tell me how many students there are. Or the university, tell me the failure rate, on average, of all students. So it's going to look through all the students and ask student to get the failure rate and then take the average. Okay? So here we have the class diagram. Singleton, again, I'm showing it in here using the stereotype notation. I'm saying this is a stereotype. Inside this, we have two methods. We have two things. One method, get instance. One attribute, the instance. And an interesting thing, you notice that underlined. What is that telling us? Well, this is a notation used to indicate static. Okay, these are static or class methods and variables. Okay, so this is one of those, I remember I told you way back, avoid using static things. Use instance variables, instance methods. Well, this is one of those occasional cases where it is legitimate and in fact advised to use static methods and static variables. In fact, just one static method, get instance. Okay, so I can say the university get instance, and it gives me back then the instance of University of Ottawa, in which case I can start calling instance methods on it. And that instance is stored as a static variable of itself. Okay, and there's only going to be one. Okay, so get instance returns that. That's the key. That one instance is always going to be stored here, and that's the only instance that will ever be allowed to be created. So, for example, let's take a concrete case, company. Okay, I am creating a system for my company. And there's only one company here. And so what I have is I have a declaration that says I have a static variable of the company, which is instance of self, and then a method, get instance, okay, which returns the company and which is private. I might have shown this with a minus sign as well, or here I've shown it using using a stereotype private to emphasize it. So get instance is all supposed to be on one line. It just didn't fit well in the box. This is just simply saying the get instance returns an instance of company. And over here, oh, actually, I correct myself. This is two lines. Company is the constructor. Okay, get instance does return a company, and get instance is not private. Get instance is public. Company is a private constructor. Okay. Company is a private constructor. Get instance is a public static method. Over here is the code, on the right is the code for the get instance method. It says if the company is null, okay, this variable, if this variable, the company is null, okay, then call the constructor, new company, and assign it to the company. And then return it. So every time this is called, the first time it will do this first if statement and actually create the instance. Second time and subsequent times it will just return it. So get instance is called to get the singleton object. Right? First time it creates it, second and returns it, second time and subsequent times it just returns it. And that is how we ensure that there can only ever be one instance. The constructor is private, so we can't, outside this subsystem, create a second one. The only place where we can actually create an instance is in this get instance, and that is only done the first time, because after the first time it's no longer null. Okay. So this shows how you would ensure that the singleton remains a singleton, basically. Any questions about that? So you can see now we're moving down into design, right? In fact, this is code. Okay, the singleton pattern is a pattern that has just one object. You can actually create singletons quite readily when you're doing domain analysis if you want. They become more common, as we said, as you move into detailed design. But this piece of code is showing how you would implement the singleton when you're actually coding it up. Okay, let's move on. The observer pattern. Another design pattern, a pattern that is used less at analysis, much more when we're doing various kinds of design, trying to build the architecture for our system. Okay? It has to do with trying to separate concerns, trying to reduce what we're going to call later on coupling between two parts of a system. Okay? So that individual parts of the system can be developed individually. The context is When you create an association between two classes, the code for those classes becomes inseparable. So the code for booking knows about the existence of passenger because it has to call methods and therefore it knows about the class name. And the code for passenger knows about the method for booking and knows about the class booking. And you can't sort of develop them separately and plug them together easily. They're really tightly bound to each other inside a subsystem. They work closely together, which is okay in some cases. But what you don't want is you don't want class A tightly coupled to class B, B tightly coupled to C, C tightly coupled to E, dot, 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 Y tightly coupled to Z. What you end up with then is that all the classes are tightly connected to each other. And you can't sort of separate off a piece of the system and replace it with something else easily. And we want to be able to do that. We want to be able to have some kind of reusability. We want to be able to divide the system up into modules that can work somewhat independently of each other. Okay? Continuing with the context, if you want to reuse one class, then you also have to reuse the other. Okay? Because they're basically programmed and designed to work together. The problem is, how do we reduce this interconnection between classes? Especially when we want to separate classes among different modules or subsystems. Because remember, within a subsystem, classes can know about each other. We can use instead of using private and public, we can use the blank, and then the classes can interact with each other and access each other's data and call each other's methods freely. Across the boundaries of subsystems, across the boundaries of packages in Java, okay, we basically have to call APIs because we don't have, or we shouldn't have access to too much information in other subsystems. The main force is we want to maximize flexibility. We also want to maximize reusability. Okay? So how do we do this? Well, at the top of slide 19 is the pattern diagram, pattern class diagram for the observable pattern. Two hierarchies. A hierarchy of observable objects, hierarchy of observers. And the general concept is that the observer class at this level is an interface. Okay. So I'm showing it a bit like a hierarchy, but basically it's an interface. At least in Java, that's the way it's implemented. Okay. In C++, in Smalltalk, it would be a real class. But the key point is that as an interface, or whatever it is, it only has a method called update. Okay. Underneath this, implementing this observer interface, we have one or more concrete observers. These are the real classes, okay, that are going to be somehow connected to a set of real observable classes. So we have some observable classes that are wanting to observe the observers. Again, the concrete case at the bottom might make this clearer. Okay? So I have my abstract observable subclass forecaster. Okay? So a forecaster, it might be in a weather system, something which an object or part of a much larger system, presumably, that is going to be generating weather forecasts for a particular region. Okay, so I might have an instance of this, might be the Ottawa forecaster. So as part of Environment Canada's system, this might be the system that finally puts together and outputs the weather forecast for Ottawa. And if I ask it at any point in time what the forecast is for Ottawa in the next few hours, it'll tell me. Okay? And there would be likewise many other instances for other cities. Then we have a bunch of applications, a bunch of pieces of system, different areas, whose job is to consume weather forecasts. So, for example, one of these might be some kind of a script in the Environment Canada's web page design. Okay, so when somebody clicks on the URL to get the forecast for Ottawa, okay, in the code for the website, there's an instance of a thing called Weather Viewer that basically goes and gets the forecast. Okay? there might be several different pages. There might be another situation where there's something which is wanting to be constantly advised of new forecasts. So whenever the forecast changes, it wants to change its display. So maybe this is a website which will update itself whenever the forecast changes. You can just leave it sitting on your screen. Or maybe it's not a web-based system at all. Maybe there's another system which is involved in at the airports, so that when a pilot is about to take a flight, they can look at a little monitor and see what the forecast is. Okay, so information is fed to that. Information might be fed to systems that have to do with traffic control or snow plowing control or any other kind of business that goes on in the world where weather forecasts determine what you do today. Okay? So lots of systems all over the place need to know what the forecasts are and need to know when those forecasts changes. And you might develop new ones at different points in time. Okay? Tied in through some mechanism to the forecaster object. So we don't want to tightly tie these together. We don't want to say forecaster object has many viewers. Okay, and the viewer knows about the forecaster maybe, but the forecasters don't want to know about all the viewer objects. Okay, so the strategy that we use is we reduce the coupling by saying that the forecaster is going to be a subclass of its abstract observable. And the abstract observable, what it fundamentally knows is that associated with it are a set of observers. And all the observable abstract class knows is that it can call an update method. And some set of subclasses will implement this update method. So now we're not tying specific classes to specific classes. We're basically just saying that the forecaster, when it changes, it just says notify all instances. And the notify all instances method is going to call update in any observer that happens to have attached itself. Alright? Notify observers is the method, in fact, I'm showing on this slide. Notify all observers, notify observers. Depending on the implementation, that's how it will be done. Another thing which we will see in the implementation of observable is add observer. So there's a method there by which a new observer can add itself, say, I'm interested in forecasts. Okay, so that's public and that's called by an observer that wants to set itself up. And then the forecaster, the observable, will call notify observers whenever it has information that is changed inside itself. Right? Does this look similar to something you've seen before? It should. Where have you seen a similar piece of architecture in this course? I see some people mouthing, but nobody was brave enough to actually speak up. The OCSF, the Object Client Server Framework, and where did you see what was going on? Was it the OCSF or was it something else? Simple Chat? Can you remember the class names that were involved?
Abstract Client, Abstract Server.
Okay, well, this is a slightly more complex question. First of all, the case that I was thinking of is the case where I have in Simple Chat, okay, where I have my client, okay, my chat client calling a display method. So it's saying, I have some information, display. I don't care what user interface is actually looking at this or doing what it's doing with this display. So that's like the forecaster saying, I don't really care who's using the weather forecast. I'm just going to say, I'm just going to call this update method and all of them, whoever is out there. Okay. So it's the same general concept. Secondly, there is an extension of OCSF itself. There is an extension of the Object Client Server Framework, which makes use of observer observable, we will leave until later. It's in the book. It's described in the book. You can take a look at it there. Okay, so this pattern of separating concerns by basically, instead of having the forecaster directly connecting to the weather viewer, by having one being a subclass of observable, the other being an implementer or observer, pulls up some of those details into these superclasses or interfaces, and means that the only coupling now is at the very high level between a class and an interface. And that can be coded once, programmed once, and that's it. In fact, it's built into Java. So you never have to program this. All you have to do is to declare subclasses of observable and implementers of observer. And you get this kind of decoupled, separated behavior for you automatically. Okay? Now, some of you are going to say, well, but what, not really see why it's so useful to do this. This does add some complexity. Okay? There's a design trade-off here. There's a complexity because you have 4 classes involved, or 4 things involved, instead of just 2 if we had a direct association across. The simplification is not at the understanding level. The simplification is in the amount of code that we have, because if I didn't do this, I'd have forecaster with association to many different kinds of weather viewer that are interested in different kinds of things, and I'd have to, if I had different kinds of observers and observables, I'd have to separately program this adding mechanism, and each association would be a unique one. Basically what I've done is I've abstracted this association to a higher level, implemented it once, and then I reuse it. And that allows me to not have to program it separately and tightly tie together objects inside a system. The forecaster and the weather viewer can be in totally separate systems, okay? Because every class in the system knows about the observer interface because it's built into Java. It's just part of the Java already. And same thing with observable. Okay, so now we can put these in totally separate systems and not have to worry about connecting those subsystems together. Okay. So the anti-patterns are to connect an observer directly to an observable. In other words, to directly create an association instead of indirectly or having it inherited. And another anti-pattern is to make observers subclasses of observable. Okay, so typical mistake. Oops. Typical mistake. Make weather viewer a subclass of forecaster. That violates the ISA rule to start with. But it is a mistake people do, especially when they're starting out in the class diagramming phase. Some of these patterns are getting a bit deep. Some of these patterns are requiring you to think and really understand what's going on. So, are there any questions about this? And how many people think they really understand what's going on here? Hands up. Okay. How many people are really totally confused? Be honest. Okay, good. So we have one person who really understands, and 0 people are totally confused, and everybody else is sort of halfway, or too shy to say. That's promising. At least I don't have half the class saying they're totally confused. Okay? So, to understand this better, you've got several avenues. You can watch the video several times. You can read the book, and look at your own notes you just took. Let's move on. Delegation. Very important pattern. Delegation is. We're getting quite low into design when we're dealing with delegation. Okay? So the context is, you're designing a method in a class. You realize that in the implementation of that method, there is another class that is already doing that work for you in some other class. There's a method in another class that's already doing it. Okay? So whenever you see, I'm creating some code, and I already have a code in another class, one of your first thoughts might be, I can inherit. Okay, make the other class a superclass. Make my new class subclass, inherit the code. Done. But that isn't always appropriate. It wouldn't be appropriate if the ISA rule doesn't apply, or if for any other reason you can't make subclasses. Okay. So inheritance is a perfectly fine way of reusing, code, but it doesn't always make sense. It only makes sense when you actually do have a generalization. If you don't have a generalization, can't do it. So what do? I mean, the anti-pattern is to just copy the code. how do you effectively make use of the method? The force, you want to minimize development cost by reusing. Well, the solution is so simple. You call the method. Okay, you say, well, what's so novel about that? Why does that warrant being a pattern in its own right? Well, the answer is that a lot of people will not call the method and will not use delegation, and they will make much more complicated code. Let's take a look at some examples. Several examples here. Okay, so the abstract pattern, delegator, delegate. Delegating method calls method. Okay? And so the delegating method has typically, this is the normal delegation pattern, is that it does nothing except call the delegate method. So that's part of the secret. Part of the secret is it's a method that absolutely does nothing else except call another method. It just does one thing. You wouldn't see this outside of object-oriented code. If you were doing ordinary procedural code, this would be a stupid thing to do, because if A, all it's doing is calling B, then whoever's calling A might as well just call B directly, right? If you were just creating simple code inside one class or code in C, for example. You wouldn't ever see this where a function does nothing but one call another function. Okay. But in object-oriented context, it makes a lot of sense. Because what we're doing is the delegating method is in one class, and the delegate, which is the second class, has a method. So we're calling delegate.method. We're calling code to do the work for us that exists in another class. The power of this will become clear in a second, hopefully. Let's take an example. We have a linked list class. A linked list class is a data structure which contains a number of methods: add first, add last, remove last, delete is empty, etc. Okay? We want to create a stack class. A stack class is going to have 3 canonical operations: push, pop, and is empty. You only want to do those 3 things on a stack. Okay? You don't want to be able to arbitrarily add first or add last, because stacks, it's first in, first out, right? Put something into the stack, and the next thing you get is that same thing out. You put 2 things in, the first thing you get out is the last one you put in. And then you go push back. Okay? So, what we want to say is we want to say that a stack has a linked list as its main part. Basically, a stack is composed of a linked list. It could be some other kind of list. I'm just using linked list as an example. But a linked list provides all the implementation. It provides all of the code that actually does useful stuff, like adding and deleting and so on. The unique thing about stack is that it can only do these 3 things. So push would be add first, pop would call remove first, and is empty would call is empty. But the power of having a stack is that we can't accidentally call add last, remove last, delete in an arbitrary spot, or add after in an arbitrary spot. The stack is a powerful class, but specifically because it is restricted to only do a subset of things. But all of its code will be delegating. It will, for example, the push method will call add first. List.add first. That's it. So all 3 of its methods will be of this style. So what we now have is we have a powerful, more reusable, more safer class. Stack is a safer class to use. If what you really want to implement in your algorithm is a real stack, then call it a stack. Don't use the linked list class directly if what you have is a stack, because with the linked list class, people can introduce bugs. Later on, some programmers working with this system, and they decide that they want to start calling add last. Or they accidentally call add last instead of add first, and immediately you have a bug in your system. So create a stack, call it a stack, and let the delegation do the work of figuring out the detailed implementation methods to call. Your design is less bug prone. All right? Here's another example on slide 23. This is our old standby airline system. What if I wanted to, in booking, find out the flight number. Okay? Very common. Okay? I'm looking at my booking on my screen. Okay? It says, you are booked to fly on, from Ottawa to Honolulu at 4 o'clock in the afternoon on October, or whatever date it is. Wouldn't it be nice? Okay? What's the flight number? Okay, well, where is the flight number? I mean, I can ask the booking what my flight number is, right? It makes a lot of sense to do that. I'm displaying this information on the screen. Tell me the flight number. Well, how do I find the flight number? Well, I delegate that to specific flight. Because I don't know it. It's not stored inside the booking. It's stored somewhere else. So I pass the query to my neighbor in the class diagram. The neighbor that knows. But the specific flight doesn't even know the flight number, right? It's not stored in specific flight. It's stored in regular flight. So the specific flight, when it gets the method flight number, it also delegates a second level of delegation to regular flight. Regular flight says, oh, okay, return my instance variable flight number, or number. Returns to specific flight, returns to booking. So what I'm doing is I am delegating the responsibility to classes that are neighbors of me until the message finally gets to a class which actually can do the computation that I want. So, so delegation itself is a simple concept, that you have a method that does nothing but call another method. What is important about delegation is how you put things together to use delegation. Okay, and so we saw an example on the previous slide of using it to create a class which has a limited set of features that is therefore less bug prone. In this diagram we're seeing another feature of it. And the important thing here is the following. We want to avoid code that would look something like this. In booking's flight number, it would say specific flight dot regular flight dot flight number. Okay? I do not want to do the following. I do not want code in booking. Okay, this is bad, just so that you write that down. Okay, I don't want to say flight number return, it would probably be something like this specific flight dot the regular flight, or regular flight, call it, whatever the variables are called, dot number. Okay? This is what I want to avoid. I want to avoid dot accessing the data value, accessing the data value. I want to avoid that because, first of all, we said that you should call methods. Okay? You shouldn't be able to access. You shouldn't access the instance variables directly. So, okay, here's another possibility. Return this specific flight. Okay, I'll get a method to do that. Dot regular flight. Well, specific flight can call the regular flight method. Fine, I can do that. Dot number. I shouldn't even. I mean, maybe I have all these things as methods to get the things. Still shouldn't do that. Still bad. Even calling the methods, because these two dots here are bad. Okay. What I can do is I can have one dot. Okay. One dot is okay. I can say the specific flight, and it's a instance variable of myself, so that's okay. Dot flight number. So I can call a method in my neighbor, but that's it. I shouldn't go beyond that. I should let my neighbor worry about how it's going to pass on or delegate on the request to its neighbor if it needs to. Or maybe it can answer the response directly. So the key here is when you're designing methods that do stuff working with other classes in your class diagram, they should never access classes beyond their immediate neighbors that are connected by associations. Okay, so we want to do delegation, get the neighbors to do stuff, and if they can't do stuff, they'll delegate further. Leave it up to them. Very, very important rule for good quality software design in class diagrams. Okay, if you're using class diagram, using object-oriented design, do that. It's called, in fact, the law of Demeter. If you look in the book, there's a little side effect on that, which basically says, care about your own local world. You can access things in your neighbors. You can get your neighbors to do things for you. But as a class, you shouldn't know about what exists beyond your neighbors. And the reason why you shouldn't know is because the less that you know about as a class, the less will have to change when design changes have to be made. Okay? So if I'm making a change to a class, and I know that people have followed this rule religiously of saying accesses are only made to neighbors, then if I'm changing class A, all I have to do is to make sure that the neighboring classes are updated to correspond to the changes I've made, and I know guaranteed the rest of the system will work fine, because I know that nobody is accessing me beyond my neighbors. All right? Very important piece of wisdom in doing good object-oriented design. And delegation is one of the key things. It's so simple. It's just saying we can help out a lot of this by just having methods that call methods in our neighbors to get work done. And they can call further neighbors. All right? Any questions? Okay, so anti-patterns, overuse generalization. There's a tendency to overuse generalization. Remember I showed you that slide back, a couple of slides back, where we had stack and linked list. Classic mistake. Classic mistake in object-oriented design is to make stack a subclass of linked list. Okay? And in fact, there is a rule. Almost applies. You can, reading in English, you might say, a stack is a linked list. Why not? It sounds like it's right. You know, it's a special kind of linked list. You know, you can make a queue a linked list as well. Okay, so it almost sounds right. That's why there is a rule as a linguistic test doesn't always completely give you everything you need to know. The problem with that is that we're going to inherit a bunch of stuff we don't want. We're going to inherit add last, remove last, delete, add after. We don't want those things. We only want these three things. And so it's defeating the whole purpose of creating a stack class if we're still inheriting stuff we don't want. Okay. The other anti-pattern is the anti-pattern I showed you originally, where I had the two multiple dots accessing beyond our neighbor. Okay. Oh, sorry, that's the third one. Accessing non-neighboring classes. Okay, this is the case there. The second case is not using delegation at all, effectively. The second case is whichever code needs the flight number, itself goes and gets the flight number. So what I want in booking is to have a flight number method, so that any code that needs the flight number calls this method here, which does the delegation. The anti-pattern is every piece of code in booking that needs flight number separately goes to my neighbor to get it. We don't want that. We want if we're going to have to access outside of our class, we want one method that does that, and only one. We don't want to access outside our class more than once if we can avoid it. So we create a delegation method that does the access. It's responsible for going and finding the flight number from some other class, and we can always call it. We're not going to have several different pieces of code doing the same thing, because that is where we end up with bugs. Because you change the code in one place, it doesn't get changed somewhere else. When you change the design, you've got to change the design in several places. All right? This last little piece here is an awful lot of little pieces of wisdom that all work together, and the delegation pattern is central to all of them. All right. We will leave it there today. Thank you very much. The midterm is covering up until this point. Okay? So, the midterm is covering up until this point. You had a hand? Good job. The best of your ability before you move too far down in this list. Okay? So, we'll leave it there today, and next day, basically, we're going to be working through this process of figuring out some example classes and doing a diagram.